So basically the sum, you may have seen this in college algebra. The sum of n terms, A1, A2, A3, all the way until AN is written like this. This capital sigma where I equals 0 all the way, well, actually, let's say 1 until n. A sub I. So if you see this notation, that means you're going to go start at the index down here, 1, and then count all the way until whatever's up here, n. That'll be your sum of this A sub I. That's the notation. So where I is the index of summation A sub I is the ith term of the sum and the upper and lower bounds of summation. Or n and 1, sorry. Respectively. So real quick, let's do some simple example. So again, this is our 1 to n, our lower bound and upper bound. A sub I is the ith term, I is the index here. But once you see it, it's pretty straightforward. So if I were to say the sum from, I don't know, k equals 3 until 5 of the following, k over k plus 2, all that would mean would be you start at 3, you go all the way until 4, or sorry, 5. Does that make sense? So start at 3, go up to 5. So 3, 4, 5. Of course, you'd add these numbers up, but okay. So assume that's pretty straightforward right now. I'll skip adding fractions if nobody cares about that.
So did you use the bottom number to start at 3 and then you moved your way up to 5? Because that was the
Yeah.
top. Okay.
Yeah, exactly. This is the starting point and the ending.
Okay, cool. Thank you.
And then you plug them into wherever you have k. K is the index, right? See that? Use sigma notation. So sometimes you can go the other direction to write the sum sorry, got distracted there. So 3 over 1 plus 2 plus 3 over 2 plus 2 plus 3 over 3 plus 2 all the way until 3 over n plus 2. So what would be your formula, your summation notation? How would you rewrite this guy?
You'd have n on the top and then you have k equals 3. Like k over n plus 2 and then put n on the top of that, right?
Let's make this 11 before, make it easier here. But
Then
So you-
yeah, I guess the top would have 11 and then the bottom would be k equals 3.
yeah, but top would be 11. And the bottom, let's say, we can call it what we want. We'll say I guess, or k. Would be equal to starting point, you said 1, right? 1, 2, 3.
Oh yeah, it'd be 1.
So this is the starting point.
How did
Ending
y'all get
point.
11?
What's that?
How did y'all get 11?
It goes all the way until 11 plus 2.
Right, but how did
The
you know?
last one.
But how did you know where to stop?
So this is the question they're going to give you. That's right here.
Okay, so they automatically gave me 11?
Yeah, so let's just
Oh,
pretend
okay.
that this is a homework problem right here.
Okay, gotcha.
What would be the series representation? the
Right,
segment?
okay, cool, thank you.
Mhm. So now we need the formula, right? We got the summation part. So what would be the formula? So for a fraction. What never changed on this series?
The top number, wait, yeah, the top number.
Yeah, so that has to be there, right? Never changed. What else was fixed?
The +2. So would it be k plus 2?
Yeah, exactly. So k plus 2. So when k is 1, we get that one. K is 2, we get this one, all the way to the ending 11. Here. Does notation make more sense?
Yeah, that's better.
Now let me give you some formulas about summations. All right, so for 1 to n, if you have some constant c, if you add it n times, well, you're going to have n of them. Cn. C is a constant. So for example, if this is a sum of some number like the number 2, this would be equal to 2n. If this number was 50, and you were adding the number 2 50 times, well, that'd be 2 times 50. That's what this formula is telling you.
Is that CN?
Yeah. See, yeah. Now, if you're adding just the letter I, the index itself, it is equal to this formula. N times n plus 1 over 2. Now, if you're adding the square of the index until n is gonna be equal to n times n plus 1 times 2n plus 1. Number 4. If we're doing the cube, that will equal n squared times n plus 1 over 4. Now let's do some problems. So these can be kind of like shortcuts for you. All right, you guys cool on this page?
Can you just go back one more?
Yeah, no worries.
All right, I'm done. Thank you.
Example 3. Evaluate the sum from I equals 1 to n of I plus 1 over n squared. All right, so basically we want to apply the formula to these and simplify the problem. So first thing, since this is an I index, that means we can pull out the n squared outside and deal with it later. So now we have I plus the series. I'm gonna do 2 steps here, hope that's okay. And 1. All right, so pull out the n squared out here. And then I have the I and the 1. Is that okay? So you can separate series anytime you want, and you can factor things outside the series if it doesn't match the index. Since we're dealing with i's, those cannot come out. You can also factor constants, like if there was a 4 here, pull out a 4. So now let's apply our formulas, right? We have one for I. The sum from I to n of I would be, see what the formula says. N times n plus 1 over 2 plus the sum of 1 to n would be just 1 times n, right? Cn. So now we're pretty much done. You can combine these. Let's see here. That'd be n times n plus 1 over 2n squared plus n over n squared. I went ahead and brought the n squared back in. Now add these fractions. This needs a 2, so that'll be n times n plus 1 plus 2n over 2n squared. Okay. Combine that stuff, that'll be n squared plus n plus 2n, which is really 3n over 2n squared. So that'll give us n squared plus 3n over this. Which reduces to n plus 3 over 2n squared. So this would be the sum for up until n with this guy. But if they were to ask us, let's say for n equals 100 or 1,000 or 10,000, you can just plug it in here and we'll have the sum. Does that make sense? I'm saying if the limit went up to 10,000, I do the sum from 1 to 10,000. All you got to do is plug that number here now. So if n is equal to 100, the sum would equal 100 plus 3 over 2 times 100, which is, that is 103 over 200. This is reduced. If n is, let's say, 1,000, then the sum would be 1,003 over 2,000. Anyway, does this make sense?
Yes, sir.
Or let's talk about limits and series. I'm gonna turn the page here. You guys cool on this page? find the limit. So the limit as n goes to infinity of the sum I equals 1 to n 2 over n cubed times 2i minus 3 squared. Okay. So we can pull out the n cube, 1 over n cube, in front of the series, but we cannot pull that out in front of the limit because the limit is dealing with the n, the series is dealing with I. So I is trapped in here, n is trapped in here. That makes sense? So let's see here. Let's go ahead and pull out the 2 over n cubed. Now let's FOIL this thing out. That'll give us what? 4i squared minus 6i plus 9, right? Okay. So now let's separate each of these in by the summation and start applying the formulas. Once the formulas are applied, we'll then take the limit. So do the sum from I equals 1 to n of the first piece minus the sum I equals 1 to n this piece plus the series from I equals 1 to n of the number 9.
Would it be minus 12?
Yes, yes, it is. Thanks. Yeah, it smeared it all. Cleaning this earlier did not clean this page properly. Oh well. All right. So the formula for this guy, so let's look at the I squared formula. I squared is going to be, so 4 times n times n plus 1 times 2n plus 1 over 6 minus the I times 12. So 12 times n plus 1 over 2 plus 9n. That okay so far?
It was only 9, and cause it's doesn't have an I, right? And that's why it's just 9n.
Yeah, it's the first formula I gave you. Remember the CN? Our C is
How come the denominator for the first I guess fraction is 6?
I think that's part of the formula, right? Let me double check. Yeah, it's supposed to be over 6.
Oh, okay.
This one's over 2.
Oh, okay, I see what you're saying, because you're using that to convert them to how the equation has. Okay.
Yeah, it's this I squared is all this right here.
Right, yeah, because the regular I would have had just 2, but I square has 6. Okay.
Mhm. There you go. So at this point, I could bring the n cubed in, I guess. This will be 2 times 4, then it'll be 8 n times n plus 1 times 2n plus 1 over n cubed minus 24n times n plus 1 over, well, actually, that 2 will cancel, right? So never mind. I think I need an alcoholic next time. I'll just leave it as 24n times n plus 1 over 2 n cubed plus 9 over n cubed. So let's reduce this. This will be square, another square, square. So we get a limit of as n approaches infinity of 8 times n plus 1 times 2n plus 1 over n squared minus 24 times n plus 1 over 2n squared plus 9 over n squared. Now, do you agree that this would go to 0 when n goes to 30? This piece.
Yes.
And this guy would also go to 0 because this one is 1 degree less. The bottom is also is 1 degree bigger, right? You see that? We don't have to fold this out to see that the bottom is growing faster. Do you all see that? These are both going to go to 0. So the only one in question is this one. What is the degree of the top here?
It's just 1.
We have an n plus 1 and a 2n plus 1, right?
It'll be a square.
Yeah, that'll be the degree 2 up top. So if you don't see it, we can pull that out, right? Those limits would be 0. So it'll be 8 times n times that'll be 2n squared plus n plus 2n plus 1. Right? Multiply your 8 in there. We don't have to, but just in case. N plus 2 is 3, that'll be 24n plus 8. So what is the limit of this last piece?
Does that mean since they're equal, it'd be 16 over 1?
Yeah, it should be 16.
How do we get 16 over 1?
Whenever you have the matching, what's it called, degrees, you just divide by the coefficients.
So we just ignore the 24 and plus 8.
Yeah, these are not growing as fast. So since these are growing the fastest, we only care about those. Oh shoot, got my 6. Where'd that 6 go? That's weird. Should be 16 over 6. There we go. Any questions on this? Do they combine ideas about limits with the new stuff we're doing today? Well, let's move on to 5-4 then. You guys are good on 5-2. You guys cool on that page though? Five point four, the fundamental theorem of calculus. So similar, we've sort of talked about this already, but not the balance part. So if a function f, lowercase f, is continuous on the closed interval AB, and capital F is an antiderivative of lowercase f, on AB. Then the integral from A to B of lowercase f of x dx is equal to capital F of B minus capital F of A. Basically, you just subtract the top minus the bottom.
Is this continuing off the previous page?
No, this is a new section.
Oh, okay.
It's more related to 5.1. 5.3 will be for extra credit. I will not require you to do 5.3. But we're gonna go straight to 5.4. Evaluate the definite integral. So before, you remember when we did these, there was a indefinite, but we had to add that plus c. You guys remember that? I know that was like a week ago, I think. Okay. So it's going to be the same stuff we did on 5.1. It's just that now we have to evaluate at these bounds. Okay. The first thing is FOIL this out, multiply, or expand, whatever word you want to use. That will be 9x squared minus 6x plus 1. Then we said that we can integrate each piece separately. Do you remember how to integrate these guys? The antiderivative was you add a power and divide by the results, right? So it was, just to remind you, 2 plus 1, so divide by 2 plus 1, minus 6x 1 plus 1 over 1 plus 1. Last one, it's just a constant, so you would say plus x. And then you're going to evaluate from 0 to 4 on all 4 pieces. Sorry, 1 second. All right, so. Now these numbers will reduce, right? So let's go ahead and do that first, I guess. That'll be 3x cubed minus 3x squared plus x. So you evaluate from 0 to 4. So this is, so we've done the integration before. The new stuff is dealing with these bounds. So the fundamental theorem of calculus says you do the top first, plug in the 4 into every resulting antiderivative, then subtract by the lower bound, which in this case will be 0. That makes sense? So this is my b minus a inside of capital F. So we found capital F, meaning the antiderivative, which is this. And then we plug in b and a. So far, does it make sense?
Yes, sir.
Yes.
Let me know if there's anything weird, or if I lost you along the way, just let me know. This part is obviously 0, right? 0 times 0 times 0. 4 cubed, what is that, 64? That's 3 times 64. Minus 4 times 4 squared is 16 times 3, that's 8, right? Plus 4. Is that going to be? You guys get 148?
Yes.
Anyways, does the fundamental theorem make sense? That's all you have to do. The integral is, like I said, is pretty powerful. We're not gonna get too deep because that's Cal 2 stuff, but we're gonna at least introduce it. So let's see that. Let me show you how we can use this to find areas. You guys pull this page.
Yes.
So find the area, example 2, of the region bounded by the graphs of the equation. Equations, it's a plural. So we got y equals 2x squared plus x plus 2, x equals 0, x equals 3, y equals 0. So it helps to graph this. What I recommend is using Desmos to help you out. Let me pull it up 1 second. All right, so the first one was y equals 2 is a parabola, 2x squared plus x plus 2. X equals 0, x equals 3, y equals 0. Okay. So they're creating a region bounded by all of these graphs. So they want to know what is the area of this section in the center. So when they say find the area underneath the curve or bounded by these graphs, they mean the section in the middle of all these functions. Does that make sense? So the integral can basically help you find areas of really strange shapes, which is why calculus becomes important, right? Because we can find areas and volumes of geometrical shapes, no problem. But in real life, there's all kinds of strange shapes. So calculus will help you find volumes and areas of all kinds of shapes, which is basically what's programmed into computers that do that type of stuff for us. So this is in the background. But first we start with 2 dimensions, so strange 2-dimensional shapes. We're not going to do any 3D. That's not till calculus 3, assuming you're going there. Maybe not. Let's see here. Okay, so we're integrating the red graph here. All right, so let me do my little crappy sketch here. So here's 3, here's 0. So there's a parabola, I don't know, somewhere up here doing this kind of thing. Right. You have the line x equals to 3, blocking that off. We have x equals 0, blocking this off. We have y equals 0, blocking this off. So the section we're looking at is in here. Granted, mine's not as pretty as Desmos, but it's cool. But what I want you to see is what are the bounds of integration? We're starting here and going up till 3. See what I mean? Because we're doing dx, we'd put this function from 0 to 3. Okay, so far? Because you have to create the integral yourself using, like, graphing this or using a grapher to help you. All right, so we'll get 2x 2 plus 1 over 2 plus 1 plus x plus 1 over, sorry, 1 plus 1. 2 will be integrated as 2x from 0 to 3. So that'll give us 2x cubed over 3 plus x squared over 2 is 2x. So then we just evaluate at the bounds. So that will be this function at 3. This function at 3. This one at 3 minus that function at 0. At 0. Oops. So this will be a0. So all we have to do is deal with this. So that'll be 3 squared, 18, right? Plus 9 halves plus 6. Which is about 57 halves. That is the area underneath the parabola, bounded by those other equations. Is there any questions about any of the steps? The setup, integration, or the evaluation part?
I don't have a question about all that. My question is just about the parabola itself. So we're not dealing with the derivative anymore, right? We're just using a function and integrating it to find the area.
Yeah, we're finding the antiderivative, which is, yeah, another word for integration. So we take the function, go backwards, antiderivative, evaluate at these points, which ends up being area. So this is one of the applications of the antiderivative. Just like first derivative was, one application was rates of change, right?
Yeah.
This is an area application.
Gotcha.
That's pretty much the main ideas for 5.4. You guys have some, you guys have some questions, right, about the last chapter or something? We'll stop here on 5.4. Let me look at the schedule real quick. I think we're doing good. Yeah, that's the last section for this class. No more new stuff, no more new sections.
Oh, thank God. The end of the year.
It's the end of the class, man. It's time to celebrate.
I'm trying to like finish these last 3 weeks off so bad. I'm like, please, please.
It's time to get some shots. Just kidding.
No, for real.
Pretty soon, pretty soon.
I'm graduating this semester, so I'm ready.
Oh, that's awesome. That's
Yeah.
exciting.
Thank God.
Me too. I'm so excited and ready for this to be over.
I'm gonna take a gap. So thank God. For real.
You've been great, Professor. No offense to you, but I hate math.
All right.
Oh yeah, for real.
Math requires a different kind of work. People are not used to it. I get it.
I'm really glad that you've like tried to give us leniency on the test because I know a lot of professors that would have, and I would have just given up by now.
Yes, same here. Thank you so much.
I'm hoping, I mean, I want you all to do well. I mean, I don't want you to fail, but it's only so much I can do. Let's see here. But yeah, so next time, I guess we'll do review for the next stuff for exam 4. I think that's all there is to it. And then after that, we can review for the final, I guess. Or answer homework questions. But you guys have any homework problems you want to work on, or any review questions that are bugging you, or
I have a question about the previous exam that I just took.
Uh-huh.
I noticed that there were like two questions that weren't from any of the sections that we covered. I think someone, I asked someone else, they said that you might have counted one of those as a bonus, but not counted the other one, right?
Yeah, I think I'm gonna just give everyone credit for it, but if you spend time solving it, I'll probably give you extra points.
Okay,
So if you solved it and spent time on it, I'll give you extra credit, but if you left it blank or got it wrong, I'll just give you the points.
oh, okay, gotcha, okay, cool.
I wasn't gonna count it against, because yeah, we didn't cover, I think that
Okay.
one, there was like one or two problems.
Right, gotcha,
I just didn't want to delete the questions. So,
yeah.
well, if you guys are doing all right, you're welcome to head out. Otherwise, feel free to stay and do homework problems.
And the exam for chapter 5, did you say that one's gonna be next week?
I'll open it right now. You can take it whenever you like. It just needs to be done before the semester ends.
Oh, okay. You know what? That's even better. Thank you. Because
So-
I was like, yo, I can't remember all this stuff in 1 week. I at least need like a week and a half.
Like, I wanted it to be due before Thanksgiving, but I mean, it's up to you. You guys are adults, so you guys want to do it after Thanksgiving, it'll be fine.
That would be greatly appreciated. I mean,
So
I can
today's
do
the
that.
15th. Yeah, how about we put it on, I don't know, December 2nd, I guess.
Okay, yeah, that's a little more leeway, yes.
But just remember that the finals right after that, so
Oh, yeah, for sure. So
don't
basically,
spend
you're
too much, don't push it back too much, because we gotta spend time reviewing for the final exam.
oh no, yeah, it's kind of like going back and forth with both of the reviews.
Yeah, guess so.
Yeah, of course, for sure.
Let's see here, okay, so it's now open.
And you said whatever we make on the final, you'll replace that with the lowest grade.
Yeah, I'll basically replace one exam grade with that grade.
Okay, cool. So we'll keep 3 and whichever one's the lowest, if the exam's higher, you'll put that one.
Exactly.
Okay, cool. Thanks.
The test 3, I think, is due, let me see.
On the dashboard, it said tomorrow, but when you click on the module, it says tonight. So that was kind of confusing.
Yeah, I think I pushed it back one day. Yeah, officially it closes tomorrow night. Yeah, it's the 16th at midnight. I'll change the little title for you.
I have a quick question.
Sure. So
Is the homework being calculated in the overall grade at the moment? I don't think it's been doing that for me.
it should, but I'll check. I know it's a little, there might be some things that need to adjust.
Okay.
I'll double check that soon. You might be right.
For the reviews, that was just for practice. Are you actually counting those? Because I mean, I have the answers. I just need to make sure if it's going to be counted, I go back and make sure all of it is set.
Check. I don't think it's being counted.
Okay, cool. Just making sure.
I'm not going to at the end, when it comes to grading everything, I'm not going to, but it could be currently being counted.
Right, gotcha. Okay, because I don't remember you saying it was. You were saying, just do it. It helps you for the test, obviously.
Yeah, it looks like, no, it looks like, yeah, it's not being counted at all.
Okay, cool. Gotcha.
60% is just test 1, 2, 3, 4.
Okay, cool. Not a problem. Thank you.
20% is all your homework stuff. Yeah, all the homework assignments.
Awesome. Cool. Great.
And then the final. You guys have any other questions?
think that's it.
All right, guys, well, I'll see you Wednesday. Oh, by the way, before you leave, I mean, you guys haven't been coming, but just in case you decide to come, Wednesday, I'm gonna be doing Zoom from home, so don't come to